In 1986, a helicopter tore across the English countryside at 249 miles per hour. During testing, the windscreen had imploded 3 separate times. The engineers replaced it with a thicker one each time and kept going. That flight set the absolute world speed record for helicopters. 40 years later, not a single helicopter on Earth has beaten it. Cars got faster, trains got faster, planes got faster, helicopters didn't. And they can't, not with a conventional design. Because the thing stopping them isn't the engine, the materials, or the courage. It's the rotor blade itself. Think about that for a second. In 1986, the average performance car topped out around 150 miles per hour. Today, a Tesla Plaid does 200. In 1986, the fastest train ran about 200 miles per hour. Today, maglev trains hit 370. Commercial airplanes, okay, they're still stuck at 600, but at least we know why. Helicopters, the Black Hawk, the Apache, the Chinook, the machines the US military trusts with combat, medevac, and special operations, cruise at around 170 miles per hour. That's slower than a Cessna, slower than a 1970s Porsche on the Autobahn. And the absolute fastest any conventional helicopter has ever gone is that 40-year-old record, 249 miles per hour. You'd think with 4 decades of better engines, better computers, better materials, someone would have cracked that number by now. Nobody has, and most engineers will tell you nobody ever will. At least not with a machine that looks like a helicopter. Most people assume there's one simple reason. There isn't. There are 3, and they're all fighting each other. The engines on a modern Black Hawk produce over 3,600 horsepower combined. A Chinook has nearly 10,000. These aren't underpowered machines. A helicopter engine could easily drive the airframe faster, if the airframe would cooperate. The problem has never been a lack of power. Helicopters have more engine than they can use. The physics breaks long before the fuel runs out. Okay, maybe the rotor blades just can't handle the stress. At 250 miles per hour, the forces on a spinning blade are enormous. Centrifugal force alone pulls each blade outward with tens of thousands of pounds of force, while aerodynamic loads try to bend it in every other direction simultaneously. But modern rotor blades are made of carbon fiber composites and titanium. They're some of the most heavily engineered structures in aviation. The Lynx that set the 1986 record used experimental burp blades, British experimental rotor program, designed specifically to handle extreme speeds. Those blades work, the materials held. If stronger blades were the answer, somebody in the last 40 years would have built them. This is where the Lynx story gets interesting, because yes, flying at 249 miles per hour in a helicopter was genuinely terrifying. During the speed runs over the Somerset levels in England, August 1986, Chief Test Pilot Trevor Egginton and flight test engineer Derek Clues flew a machine that was actively trying to shake itself apart. The windscreen imploded 3 times during the testing campaign. Each time, the engineers fitted a thicker one and sent them back up. At maximum speed, the rotor blade tips were approaching the speed of sound. The entire airframe was vibrating in ways the designers hadn't predicted. They stripped off antennas, windshield wipers, steps, anything that created drag. They bolted on a completely different tailplane from a larger helicopter just to keep it stable. And they did it. 249.09 miles per hour. Still the fastest conventional helicopter flight in history. The machine is now in a museum in Somerset. Nobody's come close since, so it's not about courage and it's not about danger. Those pilots proved the machine could survive 250 miles per hour once. The question is why nobody can go faster and why nobody can sustain even that speed in normal flight. The answer starts on the other side of the rotor disc. Now we're getting close. And if you watched our video on why airplanes can't fly past 600 miles per hour, this will sound familiar. When a helicopter flies forward, the blade moving in the same direction as the aircraft is called the advancing blade. Its tip speed is the rotation speed plus the flight speed. On a typical helicopter, the tips are already moving at 400 to 500 miles per hour just from spinning. Add forward speed on top of that, and the advancing blade tip approaches the speed of sound. You already know what happens there. Shock waves form on the blade surface. Drag explodes. The same transonic wall that keeps airplanes below 600 miles per hour hits helicopter blades at a fraction of the flight speed, because the blade tip is moving so much faster than the helicopter itself. So yes, advancing blade compressibility is a real speed limit. But if that were the only problem, you could slow down the rotor and compensate with a bigger disc or more blades. You can't. Because while the advancing blade is going too fast, the other side has the opposite problem. And this is where helicopters become fundamentally different from every other flying machine on Earth. In forward flight, the blade on the opposite side, the retreating blade, is moving against the aircraft's direction of travel. Its airspeed is the rotation speed minus the flight speed. So while one blade is going too fast, the blade on the opposite side is going too slow. Too slow to generate lift. Imagine running on a treadmill while trying to throw a ball forward. Your arm on the side moving with the belt swings too fast, while the other side can barely move at all. That's your rotor disc in forward flight. The rotor compensates automatically. It increases the retreating blade's angle of attack, tilting it more steeply into the airflow to maintain lift despite the lower speed. Think of it like tilting your hand further and further into the wind while driving. At some point, the air can't follow the surface anymore and just breaks away. That breakaway point is the stall angle. Past it, lift collapses on one side of the disc. Engineers call this retreating blade stall, and it's the primary speed limit for every conventional helicopter ever built. But it gets worse. At high enough forward speeds, the inner portion of the retreating blade isn't just slow, it's moving backward relative to the air. The flight speed actually exceeds the rotation speed of that part of the blade. The airflow reverses direction entirely. An airfoil designed to generate lift in one direction now experiences air flowing over it the wrong way. It produces negative lift, a downward force, on one side of the rotor disc. So here's the complete picture. At high speed, a helicopter rotor is dealing with three simultaneous contradictory problems. The advancing blade is approaching the speed of sound. The retreating blade is stalling from too little airspeed. And the intersection of the retreating blade is pushing the helicopter down from reversed airflow. You can't speed up the rotor to fix the stall. That pushes the advancing blade past the sound barrier. You can't slow it down to fix the compressibility. Every adjustment you make to solve one problem amplifies another. Engineers measure this trap with something called the advance ratio, the ratio of the helicopter's forward speed to the tip speed of the rotor. For most conventional helicopters, the maximum advance ratio sits between 0.3 and 0.4. Push past that, and the retreating blade enters stall and reverse flow simultaneously. That ratio is why every conventional helicopter, no matter how modern, hits a wall in the same narrow speed band. This is why the speed limit isn't a number. It's a geometry. As long as you have a single main rotor spinning above you, you're trapped between three walls, and 250 miles per hour is roughly where they all close in at once. So is this it? Are helicopters stuck forever? Not exactly, but the only way past 250 is to cheat. To build something that isn't really a conventional helicopter anymore? The Sikorsky X2 uses two main rotors spinning in opposite directions on the same shaft, coaxial rotors. This cancels the lift imbalance between advancing and retreating sides, because each rotor's weak spot is covered by the other rotor's strong spot. Add a pusher propeller on the tail for forward thrust, and you can unload the rotors entirely at high speed. The SB-1, Defiant, built on this technology, hit 284 miles per hour in level flight. And Bell's V-280 Valor, a tilt rotor that tilts its entire rotors forward to fly like an airplane, reached 345 miles per hour and won the US Army's contract to replace the legendary Black Hawk. But notice what happened. Neither of these machines is really a helicopter anymore. One is a coaxial compound, the other is a tilt rotor. To beat the speed limit, they had to abandon the shape that caused it. The US Army understood this. Their entire future vertical lift program was built around the idea that the next generation of military rotorcraft would need to break free of the conventional helicopter's physics. The conventional helicopter, single main rotor, tail rotor, has hit its evolutionary ceiling. And it hit that ceiling 40 years ago over a field in Somerset with an imploding windscreen and a pilot who wouldn't quit. Next time you see a helicopter overhead, you're watching a machine that's nearly as fast as it will ever be. Not because we can't build better engines or stronger blades, but because the spinning disc above it is fighting itself on every side, with every rotation, at every speed. In 1986, Trevor Eggington proved you could push a helicopter to 249 miles per hour. 40 years later, nobody's topped it. Sometimes the fastest you'll ever go isn't limited by technology, it's limited by shape.